Hello, my name is Benjamin Nunez. On this quick tutorial, I will be going over on how to design a low-pass Chebyshev filter. Here we have some of the characteristics that make this filter special, such as a steep roll-off. Sailing key circuits are used in Chebyshev filter design, each accounting for 2 poles. We can also see the use of the operational amplifier. Here we have the transfer function for a Chebyshev filter. As we can see, we will be dealing with complex numbers, j omega, that will be used to calculate the filter's pulse. Here we have the magnitude versus frequency diagram for a low-pass filter. The first frequency we approach is omega p, followed by omega s. We can also see the minimum attenuation and the maximum ripple, all of which are desired parameters. Moving on, these are formulas that we will be programming into MATLAB. I will be going over each one of them in more detail, but you can always pause this video if I'm going too fast. Be very careful when typing these functions into MATLAB. Any mistake can cause your program to fail. If you're ready to program, let's get started. First, you will need to open MATLAB. Then you will need to create a new function M file called Chebyshev. The inputs will be our system parameters, f of p, f of s, a max, and a min. This part of the code will be used to calculate the order filter number. For this type of filter, we have to use MATLAB's built-in function called ceil to round up the order number n if it turns out to be a decimal instead of a whole number. This is how your code should look like. The next equation we'll be programming to MATLAB is the pole equation. Calculating our poles is one of the most important parts in filter design. If our poles turn out to be complex, we can be sure that our system is stable. Be careful when typing in your hyperbolic sign and your inverse hyperbolic sign. Notice we're implementing a while loop in this part of the code. We now move on to the amplifier's gain. Remember, if this tutorial is going too fast, you can always press pause. Here we are also using a while loop for our code. It simplifies things. In our design, we want the capacitor value to be very small. We set the capacitor value to be 0.1 nanofarads. Now we plug in the formulas for the component values. Omega equals 1 over RC is useful to calculate our resistance since we have our capacitor value and our frequency. This will be a good time to save your program. Click File and press Save. Now that we are done with our code, we can move on testing our program. Let's try testing the following values. From the command window, we type in our function name as well as our parameter values, f of p, f of s, a max, and a min. For more results, you can see the capacitor and resistor values, as well as the gain and the poles. From our hand-calculated results, we can see that the results are almost identical. Now that you have your program built, you can test other values. Enjoy!